So we have to focus on insertion and deletion. So let's look at insert first. So we will so recall, how did insertion work first? We search for, so if you are trying to insert a new value x or maybe a key value pair, right, x comma some value, our focus is just on the keys. So basically we'll first search for x and do whatever we are doing earlier and put it wherever it is supposed to be. The problem is that this might end up violating the structure of an AVL tree, which means we need to rebalance. Now empirically it turns out that most of the times, more than 50% of the times, an insert operation is not going to violate the structure of an AVL tree, because if, let's say, P is the parent, right, maybe P already had a child C, and this is where we end up inserting X, right? So if this happens, then this, even if whatever be the shape of the tree around it, this will be okay, because the balance factor for P would have changed. It was earlier +1 before X was added, now it's 0. The height of the subtree rooted at P has not changed. It was 1 before, now, I mean, it was 2 before, it's still 2. So this is not going to require rebalancing. Not every insert is going to require rebalancing. But there is a significant chance that something could go wrong. And let's see, do I have examples? Well, actually, first let's try to understand the simplest example that is possible. So suppose X was added as the left child of its parent P. What is the balance factor of X going to be after insertion? The balance factor of X, because X is a leaf, is going to be 0. So there's no violation at X itself. What is the balance factor of its parent going to be? So that depends on whether the parent originally had a right child or not. Right, and whether X was added as its right child or left child. So the balance factor of P either was 0, or it was in this diagram, or it was, if it had a right child, its balance factor would have been -1. But if it was 0, after adding X, it would have become +1. And if it was -1, then after adding X, it would have become 0. The new balance factor would have become 0. Does that make sense? There is a symmetric case like this. If X was added as the right child of P, maybe it had a left child or maybe it didn't. We don't know. The balance factor of this parent, if it had a left child, sorry, if it didn't have a left child, its balance factor originally would have been 0 because P would have been a leaf node. And now by adding X, its balance factor becomes -1. If it had a left child already, its balance factor must have been +1 initially. And then when we added X, it became 0. But in either case, the parent itself is not imbalanced. There's no way the parent itself can be imbalanced. Now, in these two cases where the balance factor has become 0, it was -1 or +1, but it's now 0. The height is unchanged. The height of the subtree rooted at the parent, right? Height of the subtree is unchanged. And because the height of the subtree is unchanged here as well, there are going to be no repercussions further up in the tree. Right? Because for every other node in the tree, if you imagine, the size, or sorry, the height of the left and right subtrees for any other node have not changed with the addition of X. In this case, when the balance factor of the parent is 0. In fact, it's generally going to be true that when some change is made and well, I'll come to that later. It might not make sense right now. But does that make sense that if the balance factor of the parent changes from -1 to 0 or 1 to 0, we stop there. There's nothing to do. We know that it's not going to cause an imbalance anywhere. So what we are doing now is we are following up the insertion procedure that we had in the binary search tree with now a follow-up and a follow-up examination of that entire sequence of ancestors from X all the way up to the root, and we are going to track if at any of those ancestors something goes wrong, because now X has been added as a descendant. Maybe so the subtrees, either the left or right subtree to which X belonged for each ancestor, that subtree's height there might be a change in the height, and that change in the height might cause some of those ancestors to become imbalanced, in which case we have to figure out what to do. But at least the parent is not going to be imbalanced. And in fact, if the parent becomes balanced, then we are guaranteed that all ancestors will be fine. There will be no repercussions on ancestors above. So we can stop. Now, what if the parent has a balance factor that becomes it was 0 and now it becomes +1. It was 0 because it had no children, and now X has become the single child of P. So in this case, in these two cases, height has increased. The height of the subtree rooted at the parent has increased by 1. Even though nothing went wrong at the parent itself, we do have to look further up to see if the grandparent, can something go wrong with the grandparent. Look further up. to see if there are any repercussions. So let's see, what could the grandparent, what could go wrong? Could anything go wrong with the grandparent? So let's say this is X and X is the left child of P.
You probably need to reshare your screen.
Oh, did you not? Okay. So this is what I wrote uh, in red. When the height of the parent increases, that is when we have to look at repercussions further up on any of the grandparents. So now, what could the grandparent look like? Uh, so there are these two cases, right? Either X was inserted as the right child of the parent, or it was inserted as the left child of the parent. And we are assuming that the parent had no other child. So the height of the parent has gone up. It was 0 earlier, it is now 1. The balance factor has become +1 in this case, -1 in this case. Now, the grandparent itself, there are two possible cases here. One is the parent is the left child of the grandparent, and the other possibility is that the parent is the right child of the grandparent. Here also, maybe the parent is the, actually, let me make the symmetric case here. Maybe the parent is the right child of the grandparent, or maybe the parent is the left child of the grandparent. Now, before X was inserted, maybe the grandparent had uh, a child, right? Maybe there was um, so in other words, let me put it another way. What was the balance factor for the grandparent before X was inserted? It could have been +1, could have been 0, or it could have been -1. These are the three allowed balance factors if it's an AVL tree. Now, what if it was, let's say, -1 and adding X made it become 0? Okay, maybe the balance factor was -1 because just because there was, a subtree here of height 2. So the balance factor at the grandparent before X was inserted, before this node was inserted, would have been -1. But after this node was inserted, it becomes 0. There's no problem at the grandparent. The height of the subtree rooted at the grandparent has not changed, which means the grandparent, not only the grandparent is fine, all the ancestors above will also be fine because the height of the subtree at the grandparent hasn't changed. So no, there won't be any further repercussions. It's similar to this case where if we look up at an ancestor and we find that the balance factor after insertion has become 0, that means that ancestor was a little skewed earlier, and now adding X has made things perfectly balanced. So it's not obviously changed the height. There won't be any further repercussions. We just stop. But if the balance factor becomes +1 or -1, right? Maybe it was 0 earlier, and now it becomes +1 or -1. That means the height has increased. The grandparent is still fine. +1 and -1 are still allowed, but the height has increased. So we have to look at repercussions further up. So let me write this down, because this will actually give us a peek into what to do in general. For the grandparent node, if the new balance factor is equal to 0, stop, right? No further repercussions. If the new balance factor is +1 or -1, means height of the subtree has increased. Look for repercussions further up. The third case is where the new balance factor could have become +2 or -2. And that could happen as in these 4 diagrams. If you remove x, right before x was added, it was the balance factor here was +1. Now it becomes +2. Here the balance factor was -1 and it has become -2. Here it was -1, it has changed to -2. Here it was 1 before x was inserted and now it has become 2. So all 4 of these are examples of an imbalance happening at the grandparent node. And so we want to understand how to fix this. We need to change things so that we achieve balance again. So let's look at each of these cases. Suppose we look at the first case. How do we restore the balance at the grandparent node? So in Inorder Traversal, the relative values of x, p and g are like this, right? Because when we look at the vertical protrusions, that's the order in which we will look at all those nodes. So if we want to achieve balance, we ideally need p in the middle with x on the left and g on the right. Right? That will preserve the Inorder Traversal with more balance. So we can think of transforming the left diagram here into the right diagram by doing what is known as a rotation. So we move P up and G down. When I say up and down, I'm referring to the fact that G itself would have a parent in the tree, and whatever that parent was, preserving that parent and that edge, we have changed the node from G to P. With this structure, all 3 of the nodes P, X and G have a balance factor of 0. So balance has been restored. And not just that, the height of, are there going to be any further repercussions up in the tree? Well, no, because before X was inserted, G, the subtree rooted at G had a height of 2, right? G and P itself was a height of 2. When X was inserted, the height increased, but after rebalancing, the height is again 2. So if we just focus on this local region, which was like this and which is now like this, the height earlier was 1. When we added x, height is still 1. So sorry, height 2 in terms of the number of nodes. So balance is restored and there are no repercussions further up. So that's how we handled the first case. We handled the third case here exactly like that. It's just in the it's just the symmetric case in the opposite direction. Here the balance factor became -2 with the addition of x. So by rotating things from the right side, g p x, we make p become the parent of both g and x. In terms of the Inorder Traversal, this was the order, and g, p and x, and g, p and x continues to be the order. So the previous height was 2, the new height is also 2. Right, the balance factor here was -2. Here the balance factor has become 0. So things are restored. So both this and this, they are symmetric cases. Let's look at the other two. So here we have g, p and x in both cases. Well, let's look at this one first. G, p and x. So we have g like this, p like that, and x like this. The Inorder Traversal is g followed by x followed by p. So that means after rebalancing, what we ideally want is x to be in the middle, g to be on the left, and p to be on the right. If we can do that, we would have achieved balance again. The height of the tree before was 2, the new height is 2, so no further repercussions up. The balance factor is now 0. The balance factor here was -2. Right, and everywhere else, even at p, the balance factor was 1, it's 0. But where it was violated, the first place where it was violated was at the grandparent node, and now that's restored. So this was a more complicated manipulation. We can think of it as proceeding in 2 phases. In the first phase, we rotated x like this to make it like that, and then we rotated in this direction to make it like that. Right, the first, you can think of the first rotation as a rotation of x pushing p down like that. Oh, oops, I made a mistake. This is x, and this is p after the first rotation, and then the second rotation has x pushing g down. So it's like that. So x pushes g down and brings up p. So if you have the code, if you can write the code for a rotation in this direction between p and g, and a rotation in this direction, again from p pushing g down, then you can write the code for this more complicated transformation as rotation in this direction between x and p, followed by rotation in that direction between x and g. So a sequence of 2 rotations. Or you can directly manipulate the pointers to create the final structure. And we have one more case left, which is, the symmetric case to this, which is G with P on the left and X on the right. So here in Inorder Traversal, we have P less than X less than G. That's the order. So that tells us that X will be in the middle once we have transformed. X will be in the middle with P on the left and G on the right. So the height here is 2. Height after inserting X and rebalancing is also 2. No further repercussions up. Since the balance factor is 0, balance factor here was 2. Then after rebalancing, it has changed. Now this also could be implemented as, first we do a rotation like that, which will bring us to this state where X rises up and pushes P down on that side. And then a second rotation where X rises up and pushes G down. So these are the 4 cases, and we are just going to, I'm just going to label them in the following way. Since X lies in the left subtree of the left subtree of the grandparent, we call this the LL case. This is the RR case because X lies in the right subtree of the right subtree of the grandparent. This case we call it as the RL case because from the grandparent you first go right, then you go left. In this case is the LR case where X lies, first you go left from the grandparent, then you go right. The LL case and the RR case are symmetric. What you do is, you do a single rotation, whether it's the LL case or the RR case, and you achieve balance with no further repercussions up. The RL case and the LR case involve a more complicated transformation, which you can see and implement as a double rotation. So call this an RL rotation, but it's really a double rotation. And this would be an LR rotation, which is again a double rotation. Okay, so LL and RR rotations, they are also known as single rotations. LR and RL can be implemented as 2 single rotations in sequence. Now, this is something we did for the grandparent, but we can actually do exactly the same thing for any ancestor. Once we have done this, if we had to do this single or double rotation at the grandparent, things would be over. We would stop there because the height of the subtree rooted at the grandparent has not changed. But initially what we said is, if we are in this case where the height of the grandparent has, the height of the subtree rooted at the grandparent has increased, there's no problem that happened at the grandparent itself, but maybe further up there could be a repercussion on some ancestor. So we have to keep going up in that way. So as long as we keep going up and we see that the branching factor has now become -1 or +1 of that ancestor thanks to our adding this node X, that means the height of the subtree rooted at them has changed. We need to go further up. So the very first ancestor, as we go up, where an imbalance happened, that is the ancestor where some kind of rotation has to be done. So in this example I went through in detail, we assumed it's the grandparent. But in the general case, it's going to happen at some ancestor. It doesn't have to be the grandparent. It will be some ancestor. Let me call it ancestor A. And there are, broadly speaking, two options for what could have happened at ancestor A. So A initially had a left subtree and a right subtree, potentially. Could maybe some of these trees were empty, depends on what the ancestor A is. But uh, when we inserted X, maybe I should move this here in the middle. When we inserted X, insert X. So A is the first ancestor from the bottom where an imbalance happens. It doesn't have to be the grandparent, it could be maybe the great grandparent or some node further up. So when we inserted X, we could have inserted it either in the left subtree or in the right subtree. So there are two options here. Maybe X was added somewhere here, somewhere in the left subtree. The right subtree was still the same. Or maybe X was added somewhere in the right subtree with the left subtree being the same. Now, why did an imbalance happen? Well, the imbalance happened because adding X made the branching factor for the ancestor violate the requirements of an AVL tree. Here the branching factor must have become 2. Here it must have become -2. That's why the violation happened. And this is the first place where the violation happened. Now let's look at the left case first. If the branching factor was +2, what does that mean? It means that if the height of the right subtree is h, the height of um, the left subtree has now become h+2. Likewise here, if the height is h, the height of the right subtree must have become h+2. Does that make sense? So let's look at the left case first. We can further split this up. Let me see if I can fit this all in one slide. And further split this up and ask, where did X lie in that left subtree? So we have to zoom into the left subtree. I'm going to call this node as B. Right? AL, the left subtree of A, is now being zoomed into. We see the root was B, and there was a left subtree there and a right subtree there. Right, and there was AR. And maybe X was inserted into the left subtree. Or maybe X was inserted into the right subtree of B. I'm going to have two identical cases here. I mean symmetric cases. If A was inserted, sorry, if X was inserted in the right subtree of A, let's zoom in a little more into that and see where exactly did X get inserted. Did it get inserted in the left subtree of B or in the right subtree of B? So those are the two. BL, BR, and X was inserted here. We have 4 cases. We want to examine each of them. What to do in each of them. So let's start with the leftmost case here, which, as you notice, is an LL case. Because starting from that ancestor A, we have to go down left 2 times to enter the subtree where X was added. Now, what do we do? What do we do to restore the balance? So, firstly, let's write down the heights. The height of A sub R is H. B itself is a single node. We said the height of A sub L has become H plus 2. Height of A sub L has become H plus 2 after X was added. So it was H plus 1 before and it became H plus 2 afterwards, right? Why was it H plus 1 before? It couldn't have been H plus 2 before X was added because then there would have already been an imbalance at A. It's the addition of X which led to the imbalance. So the original height was H plus 1. So that means this height, the new height is now H plus 2. That means this height must be H plus 1. Right? Because if the new height of A sub L is H plus 2 and X was added in the left side, it's that left side which must have the height of H plus 1. The right side must have a height of H. Why? Because, well, let's see. If it had a height of H minus 1, could it have a height of H minus 1? Well, no, because then if it had a height of H minus 1, then there would be a violation at B itself. Since this would be H plus 1, this would be H minus 1, the balance factor at B would be violated. So we are assuming that A is the first ancestor where the balance factor has been violated. So the balance factor at B must have become plus 1. It didn't violate. That's why the repercussions went up to A. So if the balance factor here became plus 1, the height here must be H. It also couldn't have been H plus 1 because if it was H plus 1, then this height of the left subtree of A would have already been H plus 2 before X was added. So obviously things were fine. That's what we are assuming before X was added. And so the heights of the 3 subtrees now must be H, H and H plus 1 the way we've shown. Right now, if that makes sense, then let us see what happens if we repeated the LL rotation. Right, remember what was the LL rotation? This was G, this was P, this was X. Well, we just move this, we just rotated in that direction. That means B is going to push A to go down and rise up itself. I'm just going to copy this since there is not enough space there. A, B, A sub R, B sub L, under it is X, B sub R is like that. We have a height of H here, we have a height of H here, and we have a height of H plus 1 here. So when we do an LL rotation, what do we get? we're going to get B at the top. A is going to be pushed down. The right subtree of A will be as it is when A is pushed down. Now B had a right subtree which was B sub R. Where does that go? So that has to go to the right of B. It has to remain on the right of B. There's only one place where it could go, which is here. And the left subtree of B remains where it is with X. Let's look at the Inorder Traversal here. What was the ordering here? BL. So let's write that down. We had BL, then B, then BR, then A, and then AR. That's the order in which we will touch the vertical protrusions as we are doing Inorder Traversal. And that's the same order in which we will continue to do an Inorder Traversal here. BL followed by B, followed by BR, followed by A, followed by AR. What about the heights? Let's see. A sub R is height H. B sub R is also height H. This is height H plus 1. So obviously with the ancestor node A, the height is now going to be H plus 1. That means the overall tree up to B will have height H plus 2. What about the balance factors at each of the nodes? Well, B is going to have a balance factor of 0 because the height of the left subtree is H plus 1, right subtree is H plus 1. A has a balance factor of 0 as well. And none of the other subtrees have changed. So their balance factors were not violated before, they're not going to be violated now as well. So things seem to be fine in terms of the balance factors. Has the height of the overall subtree changed as a result of this LL rotation? Well, let's see what was the height before. The height before X was inserted, right here it was H plus 1 and then it became H plus 2. That's why it was violated. So it was H plus 1 here. This was H plus 1. One more node here. So the overall height here was H plus 2. Right. So the original height was H plus 2 after X was inserted. It became H plus. It was in danger of. Yeah, the left subtree became of height H plus 2. Right subtree was H. Right. So the original height of the subtree rooted at A was H plus 2. The final height is also H plus 2. Height has not changed. Height of the subtree has not changed. This means no further repercussions up. So after a single LL rotation, balance will be restored and we won't need to do anything. Any questions on this? This was a general ancestor A, the first ancestor where we see a violation. We do an LL rotation and we can stop there. But this ancestor could have required us to climb up, all the way, to an arbitrary amount. So it would take log n time to locate this ancestor as we are updating the balance factors up the path. And then once we see the violation, it takes a constant amount of time to do an LL rotation because a constant number of pointers have to be adjusted. Any questions about LL? Yeah, Mohammed?
Hi, Omkar. Can we go to the next slide? Um, I, I don't exactly understand how that rotation happened. I I kind of understand how B how yeah it should go that way, but how does the BR subtree comes out to?
Yeah, so you have to imagine plucking it out from here
Mhm.
and attaching it to A. Otherwise, B would have 3 children, which is not allowed. So basically, this is moved. So when A comes down, this pointer is made the left, the left child of this subtree is made the left child of A.
Okay. So are we going to write down the algorithm so that we know exactly how it should be done in general cases?
Yeah, so there will be 4 cases, and in each case, I'm going to show it diagrammatically rather than write the code because the code will, it's not going to add anything more. But basically, what you have to do is when you do an LL rotation, you have to identify. um you have to identify which node you are doing an LL respect to. So if A is the node, right, and you want to do an LL rotation there. So if this diagram tells you what A dot right will be. A dot right will the new A dot right is going to become well, it's actually going to remain the same. A dot right doesn't change. A dot left is going to become B dot right, right, or A dot left dot right.
Mm-hmm.
Uh, B dot right is going to become A. That's what this shows you. B dot right was BR, but B dot right is now going to become A, and B dot left continues to remain the same. So there'll be 3 or 4 pointer manipulations you'll need to do. Also, the pointer from the parent of A to A, uh, that will need to point to B instead of pointing to A.
Mm-hmm. And it could be some more complex situations where we have to go like a lot deeper to.
No. So you'll see that with all 4 of these cases, it's just 2 level deep. You just have to look at 2 levels. LL. This case, as you can see here, is going to be LR. This is going to become RL. This will be RR.
Mm. Oh, okay, so you're saying only 2 level would be enough to.
Yeah, only 2 levels. Starting from the first ancestor that was whose balance factor was violated, that would be enough.
Mhm.
And actually, what you're doing is you first went down and you inserted X. So you are actually tracing this path up. So if you were to imagine, if you implemented this recursively, then obviously you're going back up recursively as the chain of recursion returns. If you used an explicit stack, then you are popping these nodes successively back up from the stack. So whenever you reach B from its child, you know that you have come there from the left child.
Mhm.
So you can keep updating the balance factors uh, as you go up, because if the balance factor here changed from 0 to -1, sorry, it changed from 0 to +1 or -1, that means the height of this subtree increased. So you have when you reach B, you have to update the fact that the height of the left subtree increased
Mhm.
by 1. So you have to compute the new balance factor and see whether the height of this subtree also increased. Things like that. So that's the bookkeeping that you have to do. It depends on what you're storing in each node. You could be storing just the balance factors and not the heights. Or you could be storing just the heights, not the balance factors, and compute the balance factors from the two heights. Or you could be storing both. You don't need both, but just one of them is enough. Storing the balance factor is enough because it's just a single number you have to store. If you store the heights, you'll have to store. Yeah, that would still be a single number, but uh, to find the height of the left subtree, you look up the height value in the root of that left subtree. So, so that's an implementation level thing. But either you store the height or the balance factor, and you have to keep updating them as you're going up the chain of recursion. And then when you see that the balance factor at any node has become violated, that's the A node, which you then analyze. Where did the last two nodes come from? Did they come from the left subtree of the left subtree of A? If so, we are in the LL case. Otherwise, we'll be in one of the other three cases.
I see. All right. Thank you.
Are you full?
Hey, Omkar, so just a general question. Is it not just splitting trees, which can also be done on regular or balanced binary trees?
Yeah, that's a different data structure, though. It's not. It's not this, and I don't. I remember doing split trees, but since I haven't done them recently. From what I remember, it's the amortized analysis that is log n rather than every single operation being log n, as it is here. But yeah, split trees, red black trees, 2-3 trees, 2-3-4 trees. They would all be different ways of doing balancing. B trees. Why are we focused on AVL trees? Because they are easiest to analyze in terms of the case analysis.
And when we are doing this balancing, we should do. It will always be for all four cases. It will be bottom-up approach. So
yeah, bottom up is kind of default because we are just returning back from what we did when we did the insertion. Obviously, when we were doing insertion in a binary search tree without balancing, we didn't need to store a stack, the recursion stack, because we were just doing a decrease and conquer thing, right? Just finding the spot and directly inserting X here. But here now we need to be able to go back up the ancestral chain to figure out if things are okay everywhere. And that requires us to store all the entire chain of ancestors.
Got it.
That's going to be log n though, given that the tree will stay balanced. David?
Hi, I just had a question. So at sort of that top level, on the left-hand side, you show X being added to AVL, and on the right, sort of, you show X added to AVR. Why is it only go to AVR and not AVL or vice versa?
So we add based on what the value of X was.
Right.
So wherever we ended up while searching for X, in general, we could end up on either side.
Okay. I see. So that's not two separate subtrees. That's the same subtree, the two cases.
Yeah, these are the two cases.
Okay. I guess I was thinking that was two separate subtrees. I was getting confused.
Case 1,
okay.
Case 2.
Okay. I got it now.
And then again, case 1 sub A and 1 sub B.
Sure. Okay.
Sub A to sub B.
Okay. I was just misinterpreting those. Thanks.
Uday?
Yeah, Omkar. So I'm just trying to correlate this. Say if I want to maintain a sorted structure on the disk, then like something like B trees. So then AVL will be used.
No, B trees are the best for disk-based trees because you can store many more nodes. So here, every single node, internal node, has only one value.
Okay.
So in B trees, you want to actually literally minimize the overall height, because every time you follow a pointer down this tree, you are doing one more disk access. So it's very important to minimize the height over absolute height by stuffing as much information as possible within each internal node.
Okay, got it.
Healing?
Yes, could you go back a couple slides? One more.
Here or in the other direction?
No, yes, to the left, to the previous. Yes, here. Like the height on the left, why is it equal to 2? That there, if you're referring to the height of the tree rooted at G, then that's 3.
So it was 2 before X was inserted. That's why I circled just G and P.
Oh, okay.
Before X was inserted, it was 2, and after X was inserted and rebalancing was done, it remains 2. That means whatever changes happen, that's not going to impact the managers further up.
Oh,
Right
got
there,
it.
because if effectively, the subordinate is telling them that, well, like, yeah, there was some issue that happened, but I've taken care of it. You don't need to worry.
Yeah. Okay.
At least, I mean, the manager doesn't have to lose his or her balance. That's the
Makes sense.
reason why I'm focused on the height there. Okay, now let's look at the other 3 cases. So the RR case is actually exactly symmetric to the LL case. So let me just draw the diagram for it quickly. So we have A, we have RR, so that means X is going to lie in the right subtree. X was added to the right subtree of B. BL was like this and AL was like this. A is the first node where things went wrong. What does it mean for things to go wrong? The balance factor must have become -2 at A. What does that mean? That means the height here must have been h. The height here must have been h plus 2. If the height there was h plus 2, that means the height here must be h plus 1. And it was the addition of x which caused the height to become h plus 2. Right? Otherwise, it would have been h plus 1. So, so the question is, what's the height of B sub L and why?
Must have been H.
So it can't be h plus 1 because it was the addition of x which caused the height of B to become h plus 2 and thus violate the AVL property. It could be h. Could it be h minus 1?
No, otherwise it would have been imbalanced before you add X.
Well, it wouldn't have been imbalanced before we added x, but if this was h minus 1, after adding x, B would be the first node where there is an imbalance. Right? That would have been the problem. I mean, if this was h minus 1, the balance factor, the original balance factor before x was not inserted would have been fine everywhere. But we are assuming that A is the node, the first ancestral node that violates, at which the imbalance happens. So that's why this won't be h minus 1. If it was h minus 1, then then B would have been A and not A itself. So the balance factor at B was not, it must have become -1 from 0, not -2. right? The repercussions happen only when the balance factors for all of these ancestors change from 0 to -1 or 0 to +1. This is the first ancestor where the balance factor changes to +2 or -2 in this case. At every other ancestor below, the balance factor must have, firstly, it couldn't be 0 after X is inserted, because in that case the height of the subtree would not have changed and there would not be any repercussions further up. So it must have become -1 or +1 after X was added. It must have been 0 before X was added and changed to +1 or -1 when X was added. So here clearly the balance factor here must have become -1, which is why we had to go up to look for repercussions, and then we saw this was violated. So if this was -1, uh, this whole thing is h plus 1, so this must be h. If it was h minus 1, then we would have seen a violation at B itself, not A. Okay, so given that we have settled on what these heights are, we can do an RR rotation, which means we will B will come up, push A down. So B will push A down. A's left subtree continues to be with A. B's right subtree continues to be with B with X in it. B's left subtree now can't remain with B. It still has to lie to the left of B. So there's space here. Let's put it there. Let's see, is the inorder property violated? In terms of inorder traversal, we would first do an inorder traversal of AL, then A, then we would see the nodes in BL, then we would see B, then we would see the nodes in BR, including X. Here also we do see the same thing. AL first, then A, then BL, then B, then BR. So things are fine in terms of inorder traversal. What about the heights and the balance factors? So let's put down the heights again here. This height was H. B sub L is also H. That means the balance factor at A is 0. So A is good. This height is H plus 1. So the balance factor at B is also 0, because the left subtree has a height of H plus 1, the right subtree has a height of H plus 1. So balance factor is 0. Everything is balanced. What is the height of the entire? So has the height of the entire subtree changed? Because if it has, then there might be repercussions further up. So the original height before X was inserted was how much? You can look at that from this diagram here. So this height was H, this was H, this was H, and became H plus 1. So H plus 1 plus 1 must have been H plus 2. Final height after RR rotation is also H plus 2. Because it's H plus 1 here followed by one more. So that means no further repercussions. We can stop here. So that completes RR. Exactly symmetric to LL. Right here also original height before insertion was h plus 2. Because these two had a height of h. This is plus 1 and plus 1 more. Okay, so single rotations, hopefully you can see that not just for the grandparent, but for any ancestor where there is an LL, where there is a balance factor violation and we are in the LL or RR case, a single rotation would rebalance the tree. When we look at LR and RL, that's where things get a little more complicated. So let's assume what would happen if we tried an LL rotation here. So here also it looks like the balance factor at A is plus 2, right? So things are too heavy here. So what would happen if we try to fix it with LL rotation? Let's see why that would fail before we understand why we have to do this complicated double rotation. So if we were to do an LL rotation, then B would rise to the surface and push A down. So the diagram would actually look exactly like LL, except that X is attached to BR instead of BL. So I can take the diagram for LL and ask what would happen if we did this, but X was attached to BR instead of BL. What if we tried an LL rotation for the LR case? So I'm just going to quickly redraw it. A. So now we are saying that we are inserting X here. This is the LR case. And if we do an LL rotation, then B would rise to the surface. It would be like that. A would be pushed down. A sub R would continue to be where it is. B sub L would also continue to be the left child of B, but the right child of B would be pushed here. And this is the child in the right subtree, which is the subtree that contains X. So the balance factor here was plus 2. That's why there was a violation there. If it was plus 2, that means the height here was H, and the height here was H plus 2. So if it was H plus 2 there, it must have become H plus 2 because X was added. That's why it became H plus 2. So that means this height must be H. Right? That's why the height became H plus 2. And what's the height of B sub L? What must be the height of B sub L? Well, before X was added, B must have been completely balanced with a balance factor of 0. Because if not, then if it was already if it was plus 1, then adding X would have, and increasing the height here would have made it 0. Obviously, there were repercussions up to A because the height here changed, the balance factor here changed from 0 to minus 1. If it was 0, that means without X, these two heights must have been the same. So this height must also be H. So after the LL rotation, this will continue to be H. A sub R will continue to be H. Oops, sorry. This should be B sub R. So B sub R also continues to be H. With X, it becomes H plus 1. So if you notice, what is the balance factor at B now? On the left side, we have a subtree of length of height h. On the right side, we have a subtree of height h plus 2. Still violated. So that's why an LL rotation won't fix things. Right? Just like for the grandparent case also, if we go to that grandparent case where we had an LR, if we had just done an LL rotation there, what would we have had? We would have had P at the top, G would have been here, and this X would have actually moved in the left subtree of G with an LL rotation. So as you can see, it's not going to change anything. So that's why LL rotation doesn't work in the LR case. So we need a double rotation, therefore, and let's do that double rotation where we are in the LR case. So we have to go down to the left subtree of A and then go down in the right subtree here, B sub R. This is where X is. So B sub L is here and A sub R is here. And as we saw, the branching factor is +2. That's why there was a violation here. These heights, if this is H, this whole thing is H plus 2. And this height must be, these two heights must be H, as we just argued. Because adding X is what changed the height to H plus 1, put pressure on B by making the balance factor -1, which led to repercussions on the parent A. Okay, so when we do an LR rotation, double rotation, we will do exactly what we did in the simpler case with the grandparent. We will actually, so to understand what to do, we will actually need to zoom in. So just working at a higher level is not helping. That's what we saw. If we just looked at this diagram, we would be tempted to do an LL rotation. But the fact is that B sub R, right subtree of B, has to now be split up. It has to be now split up. And so we have to actually apply a magnifying lens there and see what it looks like. So let me do that here. A, B, B sub L, same as before. But we now zoom into the right subtree of B, and we'll see some ancestor nodes C there. Sorry, some individual internal nodes C there, and it's going to have a left subtree and a right subtree. Now, what do we know about? We know this is H. We know this is H. We know. So X, by the way, could be attached. We don't know where X is. Maybe it's here. Maybe it's here. And in the grandparent's case, actually X was C itself, where there was a violation. Right, so X could also be C itself. We don't know where X is. It doesn't actually matter. It's somewhere in this blue subtree. So what we have done is we have magnified this into one more level of detail. We know that the height is of B sub r is h, and including x it is h plus 1. So wherever x is, the height is going to be h plus 1. So the overall height is h plus 1. That means excluding C, these two heights, use a different color, these two heights of CL and CR, at least one of them must be of height h. One of them. Maybe not both of them, but at least one of them must be of height h. So let me say that in general, both of them will have height less than or equal to h, but one of them must be h. One of them must be h. The other could be h, could even be h minus 1, but it doesn't matter. So let's see what happens when we do an LR rotation, exactly like we did with the grandparent. So we have to focus on the Inorder Traversal here. So B, C, so B will be followed by C followed by A. So C is in the middle, and so when we do the LR rotation, C will be in the middle. That means it will go on the top. B was before C and A was after C. The right child of A continues to be with A. The left child of B continues to be with B. Now C, what was under C is now split up between A and B. So whatever was less than C was in CL. So whatever was less than C is now going to go here. Potentially with X, we don't know. Maybe X is C itself. Or it could have gone into CR. Likewise, whatever was in CR was bigger than C, so it goes there. We don't know if X belonged to it. But look at the Inorder Traversal of this more elaborated diagram. We have BL, then we have B, then we have CL, then we have C, then we have C sub R, then we have A, and then we have A sub R. And it's the same order even if you look at this. Right? I created this ordering from here before the rotation. After the rotation also it's the same ordering. B sub L, B, C sub L, C, C sub R, A, and A sub R. Now let's look at the heights. B sub L had a height of h. A sub R had a height of h. Now, at least one of C sub L and C sub R has a height of h. Right, I'm just going to call this less than or equal to h, but at least one of them must be h. Now let's look at the balance factor at B. The balance factor at B, the left subtree has a height of h, the right subtree has a height less than or equal to h. It could be h or it could be h minus 1. Right, so we don't know what it is, but in either case, the balance factor for B would be fine. It would be 0 or +1. Likewise, for A, it doesn't matter whether the balance factor is 0 or -1, it would still be permissible. For C, the balance factor, the new balance factor is going to be h+1 on the left minus h+1 on the right. So that's 0. So in terms of balance factors, things are working out. By the way, these heights, when I say less than or equal to h, either h or h-1. They can't be h-2, because if they were h-2, if let's say one of the heights here was h-2, then the other height would be h, and there would have been a violation at C. So it's not possible, since we are assuming the first violation happened at A. So balance is achieved. What happens to the overall height? What happens to the overall height? So here we have, before X was inserted, the overall height of the subtree rooted at A was how much? It was actually h plus 2. Right, that's actually, if you go back to the diagram, you can also see that from the diagram that we are in this case. So we came into this case because the balance factor at A was 2. So if this height was h, this had become h plus 2 with the insertion of x. That means before the insertion of x, it must have been h plus 1. So with A, it would have been h plus 2. The height of the whole subtree would have been h plus 2. So what is the final height? After LR rotation, after insertion of x and LR rotation, what's the final height? So this height is h, up to here, including B and A, it would be h plus 1, and including C, it would be h plus 2. So no further repercussions. We stop here with an LR rotation. Constant number of pointer changes, and balance would be restored. And by exactly the same argument, RL rotation would also lead to the same scenario, right? It's, if you were to imagine this tree as on a transparent board, and if you were to just walk behind the blackboard and look at the tree from behind, you would basically see this, right? That's how these two cases are symmetric. So what happens after rotation? RL rotation will be symmetric to what happens after LR rotation. So I assume I don't have to draw it from scratch again unless you want me to. I'll just write here that the RL case is symmetric. No further repercussions. So that means at a high level, either with a single rotation or with a double rotation, we achieve balance and there are no further repercussions. So that means the way insertion happens at a high level is we do what we were doing before, that is, we go down, search for X, insert it as a leaf node, And then as we are coming back up the ancestral path, we update the balance factors, and wherever we see an ancestor whose balance factor has been violated, we do a single or a double rotation there, and that fixes things. It's also possible that there could be changes all the way up to the root and no violation seen anywhere. Right? The height of the overall tree might have gone up without violating any of the balance factors. So in that case, there won't be any rotations required. Rotations will be required only when a violation is observed. Any questions on insertion? Shobit?
Yeah, Omkar, could you just repeat why the branching factor, if you move to the next slide, why the branching factor for B is 0 after after doing LL?
Oh, LL?
Yeah, after doing the LR, sorry. Not the
LR.
LL.
Okay.
What, the last one. Yeah.
So when you look at the height of the branching factor for which node?
C.
See, so the height of this subtree is 1 plus the max of the height of these two subtrees, right? This is known to be h, so it's going to be h plus 1.
Hmm.
For the same reason, the height of this subtree will also be h plus 1 because this is known to be h. Even if this is h minus 1, doesn't matter. This is h, so including 8, the whole height would be h plus 1.
But after inserting X, there would be a difference of 1, right? Shouldn't be? After we insert X. Because I assume that CL and CR have the same height. That is
Not
the reason.
necessarily. They don't necessarily have the same height. They could differ by 1.
But if they differed by 1, then adding X would have been either made it to 0 or plus 2 minus 2. So in that case, it would not.
Yeah. So when they differ by 1, including x, like imagining x has already been inserted there, they differ by 1. Otherwise, yeah, if they differed by 2 after adding x, then C would be the ancestor where there would be a first violation.
Yeah, so I'm having hard time to believe. So if we exclude X, then CL and CR have the same height, right? The subtrees.
Yes.
So then how come C, the branching factor is 0? Because we have B and A as
So you have to look at what happened before we did the rotation. So before we did the rotation, if these two had the same height, whichever tree got x, that tree became higher, I mean with a bigger height. So the branching factor for C would have become minus 1 if this x was here, or plus 1 if x was here.
yeah.
So I mean you're right that the branching factor for C couldn't be 0 when x was inserted. But we are looking at the diagram here after the rotation is done.
Okay.
That's when we are saying it becomes 0 because it becomes the ancestor of this whole subtree.
Okay.
Whatever was under it. Yeah.
Yeah, I'll study offline because I still feel that CL and CR have the same height even after final rotation. And then we have an extra X.
No, not after final rotation. Before the insertion of x, they had the same height.
Okay,
After the insertion of x, one of them became acquired a height that was one more than the other, which is why this would have become plus 1 or minus 1, the branching factor here. And that's why we would have needed to look at the repercussions up.
Okay, got it. Okay, so dot means that this X lies inside that subtree, not extra. Okay.
Yeah, I have a question mark here because I don't know where, I'm not sure where it lies. It actually doesn't matter whether it lies under CR or CL.
Okay.
This analysis remains the same.
Okay, got it. Thanks.
Abhishek?
Yeah, Omkar. So
when you say that there are no further repercussions due to height being the same after the rotation, so it's basically true to say that the branching factor becomes zero at that location after rotation, right? So branching factor and height, they are interrelated, right? They are not two different things we are coming up with. Like,
Yeah, if the branching factor changed from 0 to -1, then there would be repercussions further up because the height must have increased. But if the branching
right.
factor, um, so the branching factor had become 2 or -2, and we, after rebalancing, we brought it down to 0, potentially with a new node as the ancestor of that subtree. So that doesn't really tell us by itself anything about whether the height increased or not.
Right. Okay.
So that's why actually deletion is going to be more complicated. So you'll see that even after balancing, it's possible there could be repercussions up further up.
Even if the branching factor becomes zero.
Um, I think so. I need to, yeah. Obviously, I don't have this all memorized. So as we work it out, you'll see.
Sure. Okay.
Yeah. Dinesh?
So in all this discussion, we are assuming that this tree is BST, right?
Yes.
And do we store the balancing factor for each node?
Yes.
And
So either that or you store the height, one of the two.
and then how do we decide which rotation we need?
Based on whether the value that we inserted, right? When we reach A, we are reaching it from below, right? Because we were at the level of X.
Yeah.
So what were the last two steps we took to reach A? That will tell us which of these four cases we are in.
Okay.
LL, LR, RL, or RR. So that will tell us which rotations to do.
I was thinking based on branching factor value, we decide like if it is positive, we do LL, and if it is
yeah, you can also do it that way. What you can do is you can compare X with the value of A. If X is less than the value of A, that means we must have come from X must have been inserted on the left.
The left side. Yeah.
And then you compare X with the A dot left dot dot val. If it's more than that, that means you're in the LR case, or if it's less than that, that means you're in the LL case.
Okay, got it. Thank you.
Okay, so I'm going to take a break, but I just want to first summarize that insertion overall is taking order. So the time is proportional to order of the height, and because the height of the tree is guaranteed to be order log n as long as the AVL property is satisfied, and we are ensuring that the AVL property is satisfied by making sure the branching factors are fine after all these rotations. And we also know that once we fix things by rotation, there are no further repercussions up. We just have to do this rotation, whether it's a single or a double rotation, we just have to do it once for first ancestor that where we see things have gone wrong for. And once that ancestor is fixed, because the height of that ancestor subtree did not overall change, the branching factor is fine, there are no further repercussions up. And as we are going up, updating the balance factors, we are spending a constant amount of time on each node. Even when we reach the ancestor where things are violated, whether it's LL, LR, RR, or RL rotations, each of them can be done in constant time. So overall, the time complexity for insertion is going to be order log n. Right, order log n for going down, the downward search plus the insertion, plus order log n while coming up and fixing the branching factors and doing the rotation once at most, after which we stop. So it's order log n. So let's take a break and then let's look at deletion. Let's take a 10-minute break. It's 4:13, so I'll resume around 4:23 Pacific time. Jojan, I can take your question right after the break. All right. Actually, let me just do a quick example just so that before we go ahead, just so that we understand on a small example all the 4 different cases. So let's say we are trying to build a collection on which we want to search, and the numbers come in the following sequence. I think I need to reshare.